Welcome. Today we're going to have a little fun with some data. Some of it's going to be artificial data, some of it will be genuine data. We're not going to do a whole lot of theory, but we are going to do some. In particular, we're going to introduce some theory about smoothing things, because that's often a very useful way to go exploring data to see what might be there. So, without further ado, let's look at some data. What I'm about to show you is artificial data, and we're interested in, does it show anything other than random variation? Is there any signal, not just noise? Here's the data. There's nothing that appears visually obvious, to me at least, about any kind of pattern that exists other than jiggling around in random fashion. But appearances can be deceiving. Sometimes we think we see patterns when they're not really significant. Sometimes we think there's nothing visible, but there's actually something that's quite demonstrable. One of the ways to start exploring data, especially when it's not obvious what's going on, is to try very simple models. The simplest model of all in almost all cases is a straight line. And when it looks like there's nothing going on, this is often the first attempt that you'd make to see if you can find any change over time. If I fit a straight line by linear regression, least squares, the estimated slope is 0.00111. The uncertainty in that slope is 0.004993. It gives me a test statistic of 2.224, and the associated p-value is 0.0263. All of those came out of the computer program I used to compute the regression, which is R. Now, a p-value of 0.0263 is less than 0.05. That means that, yes, it is significant at the 95% confidence level, so I come to the conclusion that, yes, there is a linear trend. At least there might be more pattern. Now, that particular trend isn't very large compared to the noise. In fact, if we look at what the model looks like, the line, compared to the data, we'll see that that model is not really very impressive, whatever impressive means, but at least it is real. Well, so there's some kind of change over time, and it seems to be going up. It might even follow a straight line. But is there more? Well, one of the things that's always worthwhile doing is, when you have a model to fit some data, subtract the model from the data to get residuals and look at the residuals. Also, you'd be interested in whether or not they're white noise, because statistics, like the statistical significance of that straight line fit, are usually based on assuming that the noise is white noise. So some good ideas are to plot the residuals and look at them, almost always an important step, and take those residuals and use them to compute the autocorrelation function to see whether or not they might actually be white noise. Here are the residuals. They don't look much different from the original data because the signal we found, the straight line, wasn't very big. I don't see anything visually obvious that represents pattern other than what we've already identified. If we compute the autocorrelation function of these residuals, we see that the autocorrelation function at lag 0 is equal to 1, as it must always be and will always be. That's no surprise. But for lags greater than 0, all the autocorrelation values are small. In fact, they're within the range we might expect from natural variation, which is indicated by the dashed blue lines above and below 0. I also ran another test. It's called the Box-Young test for the autocorrelations as a whole, and it too told me there's no evidence of any genuine autocorrelation. Yes, these noise values are plausibly white noise. That means that our statistics for our straight line fit can be relied on, what came out of the computer program, because that's based on the assumption that the noise is white noise. Well, that doesn't mean that's all there is to the signal. There's nothing obvious in the residuals, and the autocorrelation function appears consistent with white noise, but there might be more signal there. It might be just very small or subtle. We can look for more using analysis. If you've already fit a straight line, you might find there's a linear trend. Well, maybe there's a more complicated trend. A natural next choice would be to try a quadratic function of time. Well, I fit a quadratic function of time to these data. The p-value came out as 0.9419, which is not less than 0.05. It is not significant, not even close. And if we look at the plot of the new model, the quadratic model, it really looks a lot like the linear model plot. My conclusion is there isn't any significant quadratic term. But that doesn't mean that there's not more signal present. Maybe there's some more complicated signal. Let's look for more. We could try a cubic function of time. And when I fit a cubic function of time, this time the p-value for the cubic term came out as 0.0247. And once again, that is significant. So it's looking like maybe the signal behind these data are either a cubic polynomial or are very well approximated, very close to a cubic polynomial. Here, by the way, is the model I got. You'll notice it's not very large. It's not impressive. That's because the noise is so big. The signal is there, but the noise is quite big compared to the signal, so there's a low signal-to-noise ratio. So the signal does not look impressive when we plot it with the raw data. Now we tried a cubic polynomial after a quadratic polynomial after a linear polynomial, a straight line. We could also try a quartic polynomial or a quintic or polynomials of degree 6, 7, 8, etc., etc. is how we want to go. At each step, we can test whether or not the new terms improve the fit with statistical significance. This procedure of adding more and more explanatory variables and seeing at each step whether it improves the fit is something known as stepwise regression. We can plot the statistical significance, the p-value, that we get of the new term for each polynomial degree. And when I do that, I get this. A degree 1 polynomial, that's a straight line, gave me a statistical significance which is less than 0.05, a p-value, so it's significant. The degree 2 polynomial, the quadratic term, did not give me a low p-value. It's not significant. The degree 3 polynomial, that new term gave me a statistically significant fit. So that means that a cubic is probably a realistic model. If I tried polynomials of degree 4, 5, 6, 7, 8, 9, 10, none of them gave me a statistically significant fit. So none of those extra polynomial degrees seem to be doing a good job of modeling the data. And it's starting to look like a cubic polynomial is the best model we're going to get from these polynomial attempts. By the way, only degrees 1 and 3 are significant, so we really should stop with our cubic polynomial. I will also note, there are some dangers with stepwise regression. The main one is, in stepwise regression, we keep adding one more and then one more and then another explanatory variables, so we end up building a lot of models. Well, if we build one model, the chance of its crossing the 0.05 p-value threshold just randomly is 0.05. If we build 10 models, because we tried 10 different polynomial degrees, we got a lot more chances of crossing that significance threshold just by accident. Now, because of this, stepwise regression really can be tricky and it can sometimes mislead you. Some people actually recommend just don't do it. I've found, however, that it is a useful thing, especially for exploration. Also, when you have a lot of variables that might help you explain what the target is, trying a stepwise regression can sometimes help you identify what the variables are that actually are doing the work to create useful models. So some people recommend just don't do stepwise regression. Some people say, oh, it's great. I think it's a very useful thing for exploration, but you should take the results with a grain of salt. Be cautious. Stepwise regression often involves building a lot of models, sometimes so many that you get what looks significant, but it's really just by accident. Incidentally, a specific danger for using stepwise regression with polynomials is that when we use a high polynomial degree model, the probable errors of the model values get very, very big very rapidly at the edges as the polynomial degree gets bigger and bigger. That means you might fit a high polynomial degree model, and it might be a good model. It might even be the best one because it's fitting so well to the data that are in the middle. But even though it's getting better and better in the middle, better enough to justify it, it will be getting worse and worse at the edges. Polynomial models are really good for approximating what's going on in the middle of the data that you're looking at a time series. But they get worse and worse and get really, really bad as you get near the edges of the time span. It's the weakness of high-order polynomial models. You might wonder, how does our cubic polynomial model compare to the true signal? Now, in almost all cases, you can't make that comparison because you don't know what the true signal is. In this case, we do know the true signal because this is artificial data. I constructed it, so I know exactly what the true signal is. And if I compare the model we got to the true signal, we can see they're quite close. The true signal is a cubic polynomial. The fitted model was a cubic polynomial, but it's not the exact same one because it's influenced by the noise as well. Nonetheless, it is pretty close to the true signal. So here's a case where we built a model. We did it by starting with the simplest possible model, a straight line. Then we made the model more and more complex by adding polynomial degrees. We stopped at polynomial degree 3 because that was the best that seemed to be working for us. And we find out that it fits really well. Don't expect results to be this good all the time. A lot of the reason this model worked so well is that the actual signal was really a cubic polynomial. That happens very rarely. Usually the signal might be well approximated by a cubic or some other polynomial, but it's not exactly equal to one. So I guess the object lesson is, this case worked out pretty well, but this case was artificially created to make it work out pretty well. Don't expect it to happen that well all the time.